Greetings and welcome, friends. We're looking at page 481. We were talking about polynomial functions and some of their different features, I guess I'd say. And here's problem 2. It says, describe the characteristics of the graphs of odd degree and even degree polynomial functions whose leading coefficients are positive. So let's consider some of these. So I'm going to do odd degree over here and even degree over here. And let's see if we can find a trend. So let's see, odd degree, that would be like y equals x to the 1, right? Or f of x equals, x, yep. So that's 1. What about x cubed? What was an x cubed? It would look kind of like this. All right, something to that effect. And then x to the 5th would look kind of like this. Something like, right, 1, 2, 3, 4 bends. Thank you. Right, so that's what those would look like. Let's look at even degree. So let's see, y equals x squared. Would have been a plain old vanilla parabola. A fourth degree polynomial might have looked like this. And a sixth degree polynomial might have looked like this. So what do all of the odd degree polynomials have in common? Yeah, their end behavior is the same.
One that's like a straight line across.
The green one there? Oh, the constant? Yeah, the constant one doesn't necessarily, it's kind of like a degenerate case. It's just like so reduced and simplified that it doesn't necessarily apply to all of these. But the end behavior is the same. And notice that's also true for the evens. So let's see. Let's actually make a generalized statement here. So a positive odd, positive leading coefficient, has the following end behavior, where, let's see, f of x approaches negative infinity as x approaches negative infinity, right? And f of x approaches positive infinity, so y is increasing every time x increases, right? So basically this is math speak for when you go to the left, it's going down, and when you go to the right, it's going up, right? That's kind of what that's saying. Similarly,
and behavior is saying positive odd, what does that mean?
positive odd, so positive leading coefficient, but an odd degree. So let's consider what positive even would be. So in this case, all of these open up, right? If I want to use that parabola kind of language that we're used to. So I would say that f of x approaches positive infinity as x was going negative. And f of x approaches positive infinity as x approaches positive infinity. So when I go to the left, I'm going up. When I go to the right, I'm going up, right? Now, what do you think would happen if I changed the leading coefficient to being a negative? Yeah, it would actually just flip these over. So, for instance, my line would be flipped like this. My third degree would be flipped like that. My sixth degree. And the end behavior would just flip-a-roo. So this would become positive, this would become negative. What's up, Hank? Rapido.
Wait, what is it? What you said is that 9.5, that's a 9.5? Or as? Oh, it's as.
Yes, I see what you're, yep. My A does look like a 9 there in some cases. So in general, we can kind of have those results that you know, all of the even degree polynomials have the same end behavior. All of the odd degree polynomials have the same end behavior. And then you just flip them, right? So upside down parabola, when it's negative, upside down fourth degree becomes a letter M, right? Upside down fifth degree, or sixth degree, sorry, right? Then all of their end behavior would just go negative anytime it's negative, right? So that's the idea. So let's look at another problem. We'll have catch it later in a second at the end of the video. I'll go back to it. Let's see, problem 10. It says identify the polynomial function as linear, quadratic, cubic, quartic, or quintic. State the degree and how many real zeros are possible. So I just actually want to analyze this in all possible ways. So let's see. What's the degree here? It's third degree. So the name of this would be what? It's cubic. And in fact, it also has 3 terms. So I could describe this as a cubic trinomial. But the trinomial part isn't as significant these days. The leading coefficient is what? And it's positive. Leading co is positive 6. So it's odd degree, right? Positive 6 leading coefficient. Let's see. How many roots do you think this could have? X-intercepts. 3. It's the same as the degree. Or it could be 1, or it could be, or it could be 2 or 1. All right. But the maximum number of roots or x-intercepts is always equal to the degree of the polynomial. All right. And then how many bends was my word to describe when it completely changes direction from going positive to negative. And that would be 2 or 0, right? So that is 1 less. Let's see. So this is same as degree, which is what we learned the other day. And this is 1 less than the degree. Right? And let's talk about end behavior for this. End behavior. So let's see, it's an odd degree. So odd means that the end behavior is going to be in opposite directions, right? Whoa, whoa. Right, so opposite directions for the end behavior. And it was a positive leading coefficient. So in fact, the end behavior is going to be, actually I can just snapshot it this way, can't I? Bam, how great is that? Lazy man's way of giving notes. Right there. Right? So because it's an odd degree and positive leading coefficient, right, it's going to be like a y equals x graph, where it's negative on the left, it's negative when x is negative, and it's positive when x is positive, right, is the idea. And actually, just so you can see what this looks like, let me see if I can quickly, rapido, open up a graph of this, and let just see what our situation appears to be. So let's graph this. This is 6x cubed plus 8x plus 7. And, all right, that's kind of hard to see what's going on here. Actually, I'm going to change this to a rectangular grid. So I'm going to distort it, but let us see what's going on here a little easier. And I'll make this medium. So looking at this graph, let's see if we're right. Right, so I changed my scale a little bit and paste. And let's just see what we got. So let's see, number of roots. I said 1, 2, or 3. How many roots does the graph actually have? 1, right? 1 x-intercept right there. How many bends? I said 0 or 2. I would classify this as 0 bends, right? It never actually had a hill or a valley, like it never had a maximum or a minimum locally, right? It was increasing more slowly for a minute, but then it kept increasing faster, right? And let's see, end behavior. As x was going negative, y was going negative. As x was going positive, y is going positive. So it appears as though that is the situation, right? So it was this situation was 1 root 0 bends. But you don't have to know all that. You just have to be able to analyze based off of the equation and know what the maximum number of those things were. And eventually we'll talk about actually finding those roots. But I think we're a couple days off from that. Let's see, last example. Let's see, problems 14 through 17. I don't think we did all of them. It said match the polynomial and its functional value. So these are all named p of x, and basically they're saying which of these would p of 4 equal negative 166. All right, so let's just look at 14. 15? All right, we'll do 15 then. 15 is p of 4. What is p of 4 equal to? So that means I would replace x, x, and x all with 4. So 4 to the 4th minus 7 times 4 to the 3rd plus 8 times 4 minus 6. And I'm just going to simplify this. Let's see, 4 to the 4th, is that 256? That it is. Oh, what do you know? 4 cubed is 64 times 7 is 448, and it would be negative. Plus 8 times 4 is 32 minus 6. So let's see, bring this all together. I get negative 166. So behold, p of 4 is negative 166 for this function, and that's why they matched it up with that. If it didn't work, I then would have tried p of 5, or p of negative 4, or p of negative 2 to figure out which one it would equal. All right. So that's the idea. You were just kind of using direct substitution, plugging in the input and figuring out what your output was for these. And by the way, you could also write p of 4. P of 4 equals negative 166 is kind of a function way to represent that. You could also write that as an ordered pair as 4 comma negative 166, meaning when x is 4, y is negative 166. And that would be the point's location on the graph as well. All right, internet friends, that's enough for now. Have a great day. Bye-bye.